Hope everybody's doing very well. We will get started soon. Hey, it's 12:30. Thank you for joining this Zoom session this afternoon. As you know, we are going to be doing this online teaching mode for this week. And then next week, we are transitioning back to the face-to-face environment. But I wanted to let you know that I will continue doing the Zoom hybrid mode as I'm teaching. So I'll be in the classroom, but I will continue doing the hybrid. So you will also have the opportunity to join via Zoom if you need to stay home. Okay, so keep that in mind. But I'll be in the classroom on next Monday. And we started last week. Last week I was in a conference, so I was not able to do the session live. But I posted the recording. So in the recording, there's an explanation of the syllabus. There's also an introduction for the class. There's information about my office hours and how to connect to my office hours and so on. Also information about the course grade and how the grades are going to be distributed. So if you have questions about that after watching the video, you can let me know via email, or you can connect during my office hours. So before I get started, I wanted to know if there's any questions. Today we're going to start with the material for the semester. And we're going to be focusing on this first part, which is looking at how the processes that are needed to develop a product and the schedules impact the layout of the facility. So this class is going to be looking at the design of manufacturing facilities from different point of view. For the first part of the semester, we're going to focus on the inside of the facility. And then towards the end of the semester, we're going to talk about the location of these facilities as part of the design. So now I'm going to start my video. I'm going to expand the slides, and let's start our discussion. So start by start video. So in every session during my class, I always like to start with the course objectives. So you keep in mind during the semester, what are the things that we are trying to accomplish. So during this semester, these are the 4 things that I want you to be aware of. So at the end of the semester, you should go through this list and you see, okay, I was able to go and develop an understanding of the principles of facilities location, layout, material handling systems. Also, I had some practice designing facilities. I also learned formulation models and analytical procedures for the study of facilities layout planning. You're also going to learn fundamental principles of material handling. And finally, you should be able to design layouts incorporating product, process, and personal requirements. For this particular lecture, we're going to be focusing on these 4 topics: product design, process design, schedule design, and facilities design. For this session, today's session, we're going to look at the first 3 topics, and then we'll continue on the next session with the rest of the presentation. In terms of the learning objectives, we want to learn the product, process, and schedule design functions as they relate to the facilities planning. So each one of these pieces, product, process, and schedule, will have an impact on the way that we're going to design our facility. And that's what we want to understand in this lecture. We want to see, okay, how is the actual product impacting or the design of the product impacting how I'm going to design my facility? And that's connected to the process. So in order for you to build that product, you have to follow a process, sequence of operations, and that will dictate also how the facility is designed. And finally, the schedule. So the schedule represents this time piece in which you, let's say you have to get at least 10 batches of a product per day. So that will impact the number of machines that you will need to be able to fulfill those requirements. Or if your level of ordering is less, you might not need that many machines. So you can see how understanding the demand, the timing is also impacting the design of your facility. And the second objective is to understand the interactions between the facilities planning and the product, process, and schedule design. So as I explained, if you look at figure 1, there's a relationship between product, process, and schedule design and facilities planning. So facilities design is in the middle of these 3 design parts. So let's begin with the product design. So in this lecture, we're going to touch on each one of them. And in the product design, this involves both to decide which products are to be produced, right? So if you are a electronics manufacturing company like Samsung, so decide which products are you going to be putting out for the public. Are you going to be doing only cell phones? Are you going to be building also TVs or tablets, or you're going to be also looking at washer machines, dryers, refrigerators? So deciding which products are to be produced is part of the product design. And then once you have made that decision, then you have to come up with a specific detailed design of the individual products. The decisions regarding the products to be produced are generally made by the upper level management. So we as engineers might not have a vote in terms of which products are going to be putting out for the customer. This is typically done based on market analysis. So from people from marketing will understand what are what is the customer needs, what are the customer needs, and how is the market in terms of being available or not for the company. So if you have too many companies already building products for a specific market, you might not want to go in that direction. But if you only have a few of them, then upper management might say, okay, we have an opportunity, we can explore that market, and we might design some products. So the design of a product is influenced by the actual product, the aesthetics, the function, the materials, and the manufacturing considerations. So that's talking about the product itself. You want to make it a product that is appealing for the customer, and that requires some level of aesthetics, functionality, materials, and altogether manufacturing considerations. So marketing, purchasing, industrial engineering, manufacturing engineering, product engineering, quality control, among other factors, will influence design of the product. So now looking at the actual design of the product, we will need some type of drawings and prototypes, pictorial representations and prototypes of the products. So those can give us important inputs as we design the facility, as we plan for the facility. So for example, here we have an exploded assembly drawing for a component. So you can see, even though it's just a single part, it has 11 components. And understanding this can give us an idea. Okay, so if we have 11 components here, can we manufacture all of them? If we cannot manufacture all of them, can we purchase them? Do we have suppliers around that can supply these components? Are these suppliers reliable? Are they going to deliver this when we need them? And so on. So there's a lot of questions that we need to ask ourselves when we're designing the facility. And we're going to touch on that soon. So understanding the prototypes in terms of how many parts and how are these parts designed and who can design and can we manufacture these parts or not. All those things are going to impact our decisions as facilities planner. Photographs and drawings also allow the planner to visualize how the product is assembled. So from this previous slide, we have now an idea of what are the components that are part of this assemble. But now in order to do the actual assembly, we need additional information. So these photographs and drawings allow the planner to visualize how the product is assembled. So if we need machines to put these parts together in order to get the final product, we need to understand how the sequence of parts is done. And that's what these drawings and photographs are providing. In addition to that, we need the detailed component part drawings are needed for each component part, especially if you're planning to manufacturing them. Also, since these are going to be assembled between, you're going to have components coming together to create a bigger part. We need to understand the dimensions at a very specific level. So these drawings should provide part specification and dimensions in sufficient detail to allow the part fabrication. Okay, so we need to understand the dimensions. Also, if you see on this figure 4 for the component part drawing of a seat, you see that in addition to the dimensions, there are a plus minus sign next to some of these dimensions. Those are the tolerances. So if your product are within those tolerances, you even though you are not, let's say for the right side part of the drawing, you have this diameter that is let's say the diameter is 0.82 and you have a plus 0 minus 0.04. So if you're in between those tolerances, your part is still good. But if you're outside those tolerances, then you might not be able to use this part to do an assembly of the final product. So the combination of explode assembly drawings and component part drawings fully documents the design of the product. So the drawings can be prepared and analyzed with computer-aided design systems. If you are not aware of concurrent engineering, this is also an area that is relevant for industrial and manufacturing engineering, which typically is looking at ways to perform tasks at the same time. So you are creating the product, getting the input and the feedback from multiple areas of the manufacturing facility. So concurrent engineering can be used to improve the relationship between the function of a component or product and its cost. In this, functions are integrated to reduce the elapsed time required to bring a new product to the market. Concurrent engineering provides a simultaneous consideration in the design phase of the life cycle factors, such as the product, design, materials, manufacturing processes, testability, serviceability, and quality and reliability. So the idea between typical engineering and concurrent engineering or the difference is illustrated in this picture. See, there's a versus here. So typically you will see in most design and engineering processes, you have this sequence type of events happening. You go from requirements, design, implementation, verification, and maintenance. So if something happened, let's say in the design phase, and you don't get the, let's say you do something here that is going to impact verification, but since you are not aware of the needs of the verification component, you move forward to implementation. And it's not until you get to this point that you realize, oh, I did something wrong here in the design phase that is going to impact my verification. So you will have to go back and redo and go through this process. So that's time consuming. With concurrent engineering, what we are trying to do is to avoid that. So we involve people from these areas from the beginning, and they're providing feedback. Let's say at the design phase, analysis and design, you're getting input from the people that are going to be doing the deployment, the testing, the evaluation, and so on. So it's a continuous loop in which you are getting the feedback that you need, and that tends to save time because that avoid these changes that can be prevented, or allow you to avoid errors that might delay the process or the final product. So any questions about what I just covered? No questions?
Seems pretty clear.
Awesome. So let's talk about process design. Process design. Here we are trying to identify required processes. For example, determining how the product is to be produced. Decide whether a part will be purchased or produced. And for parts that are going to be produced, the process designer must determine how the part will be produced, which equipment will be used, and how long it will take to perform the operation. The final process design is dependent on both the product and the schedule design. So this goes back to our initial discussion. So they're all connected. So we talk about the product. Now we're talking about the process, and then after that, we're going to talk about the schedule. So in terms of identifying the required processes, there are multiple make or buy decisions that require input from different areas in the company. And you as an engineer, you're going to be dealing with not only with the engineering department, but you are also going to be interacting with people from human resources, let's say computer science. You're going to be interacting also with marketing and so on. So most of these make or buy decisions require input from these many areas: marketing, process engineering, purchasing, human resources, among others. So for example, if you want to make a decision between manufacturing in-house a part or buying it from a supplier, you might need to get information about cost. What will be the cost for you to manufacture that in the facility, and what will be the cost of buying that from a supplier? So finance might need to be involved. Also, if you are planning to bring a new manufacturing process into the facility to manufacture these parts, marketing should be involved in order to say, okay, you're going to start building these parts. What's the market in the future? And are we going to have enough market for this part? If the answer is yes, let's move forward. If the answer is no, you might be better just getting a supplier because you're going to make this big investment, but there might not be a market in the future for that big investment. So that's the idea. So for you to come up with a make or buy decision, you need to get the input from these many areas. Human resources also is important. Like, again, if you are going to bring a new manufacturing part to develop a part, manufacturing component to the facility to build the part? Do we have the staff? Do we have the expertise? So that's part of human resources. So here's some in this figure 5. There are the make or buy decision process. So you see there's 3 or 2 big areas in this figure. On this side, you have the primary questions. Let me see if I can draw in here. So these are the primary questions. These are the questions that you are going to be asking first in order to make a decision. So for example, can you purchase the item? If the answer is no, that's simple. Then the only option that you have is to make that part for that item. But if you can purchase that item, then you can come up here into these secondary questions. And then ask the suppliers or ask the company, is the item is available? Will our union allow us to purchase the item? Sometimes you have to deal with the unions. They might not allow you to do some, might be some legal contracts that avoid you or that do not allow you to go and do these type of deals. So you need to be aware of that. Also, how good of a product are you going to be getting from these suppliers? Are the quality good? And are these sources reliable? Meaning that are they going to deliver when you need them? Or are they going to be taking you, giving priority to other customers? So those are questions. And then you move down into this sequence. Can we make the item? That's the next question. If the answer is no, then that's simple, right? You don't have the machines, you don't have the expertise, then you're forced to buy that part. But if the answer is yes, then the next question would be, is it cheaper for us to make than to buy? So can you, if you make the decision to manufacture these parts in your facility, is it gonna cost you more to do that than to buy? If the answer is no, then you buy. If the answer is yes, then you move down. Is the capital available allowing us to make? If the answer is no, then you buy. If the answer is yes, then you get to make. So there's only 2 instances in which you are going to make. First one is if you cannot purchase the item. And the next one is if you answer yes to the rest of the questions. In terms of the input to the facilities planner, what do we need as facilities planner in order to design the facility? We need a list of the items to be made and the items to be purchased. Okay, so we need both information. Items to be made because we need to design for the manufacturing piece of those items, and the items to be purchased because we also need to plan for space to store them and also to move them through the manufacturing floor. So that's where the material handling component is also relevant. So if you're bringing that from a supplier, you need to find a way to move that into the storage and also into the facility. So the listing, that list that you need as a facilities planner often take the form of a part list or a bill of materials. So a part list, figure 6, is showing you an example of a part list for an airflow regulator. And as you can see here, this is information about all the parts that are needed to assemble this airflow regulator. Okay, so you have a list of parts. Actually, yes. So the list of parts are here. And then for each part, we have a name, the drawing, the quantity that is needed, the type of material that is used, the size, and whether you're making or buying that piece. That's the information that you need for the part list. Okay, so as a facilities planner, you get this information. You say, okay, I'm gonna be creating some space to make all these pieces, or designing for the processes needed to make these pieces. And I know these parts right here, we are not manufacturing those, but I still need to consider how I'm going to store them into the facility and move them into the manufacturing floor. A bill of materials is often referred to as a structured part list. So this is, again, the previous one is the part list. This one is what is known as a bill of materials, and is often referred as a structured part list. It contains the same information as a part list, plus information on the structure of the product. So if you compare this figure with figure 6, you can say that the main difference is right here. The level is telling you, so this is like a hierarchy, right? For the final assemble or assembly is here level 0, and then a level 1, you have 2 sub components. And then for each sub component, you might have another level, right? And so on. So it gives you an idea of what are the basic components at the lower level. And as you put them together, how can you create the final assembly? Typically, the product structure is a hierarchy, as I mentioned already, referring to the level of product assembly. So level 0 usually indicates the final product. Level 1 applies to sub-assemblies and components that feed directly into the final product. And level 2 refers to the sub-assemblies and components that feed directly into the first level, and so on. So this is the figure 8 is illustrating that level 0 is the final product. And then level 1, you have these 2 sub-assemblies. Actually, this one is just a component. This one is an assembly. And then as you move down, same thing here. This is a single component, but this is another assembly at level 2, until you get to the lowest level, in which you have mostly components. Once a determination has been made concerning the products to be made in-house, decisions are needed as to how the products will be made. Okay, so this process selection procedure involves the following steps. Very elementary steps. We need to define the elemental operations. So what are the basic operations that are needed in order for you to come up with this final assembly? So for example, you might need a station for putting together some parts, but later in the process, you can use that same station to assemble another part of the product. So when I define these elemental operations, let's say I call this assembly, maybe in step 1, I'm using that station, let's say step 1, but later on in the process, let's say step 10, I might be able to reuse that assembly station to do step 10, right? So by defining these elemental operations, I'm defining these elemental operations that can be used 1, 2, 3 times in the process. We can identify alternative processes for each operation. Step 3 is to analyze alternative processes. Step 4 is to standardize the process. So standardize the process again, meaning that what are the steps that are going to, what is the sequence that is going to be followed, how long is it going to take, and so on. And then step 5 is to evaluate alternative processes. So after you have all these alternatives based on the different alternatives, right? And so I have these many options. Now I have some type of performance measure to compare them. Most of the time you're looking at time. So out of all these alternatives, which one is going to allow me to be more efficient? And that's what you're doing. In step 6, you're selecting the process that is going to be the best for your product. So the facilities planner, in terms of selecting the required processes, the facilities planner will not perform process selection, right? That's going to be information that's going to be delivered to the facilities planner. But you need, as a facilities planner, you need to have an understanding of the overall procedure, because that is going to provide a foundation for the facilities plan. So step 1 of the procedure involves the determination of the operations required to produce each component. And in order to make this determination, alternative forms of raw materials and type of elemental operations must be considered, which is what I explained in the previous slide. So these elemental operations, let's say assembly or painting or cooling or putting in an oven, these elemental operations can be reused at multiple areas of the process. But we need to consider alternative forms. So if you need to put these parts in an oven or you need to heat them, can you use an oven, or do you have any other machine that can do that, a blower or something like that, that can help you get the parts to a specific temperature? And they consider the benefits and costs associated with those alternatives. Step 2 involves the identification of various equipment types capable of performing the elemental operations. So you have options that are manual, mechanized, and automated alternatives should be considered. Manual labor typically is less expensive when you compare us with a automated alternative, which requires the purchase of a robot and so on. So timing is important. Like if you're going to be performing these operations for a long, let's say 30, 50 years, and maybe consider an automated alternative will be an option. But if you're just doing this for a year, 2 years, you don't want to make that big expense investment into a machine. Maybe a manual operation, like having an operator doing the process manually, will be an option. Or mechanized, which is a combination of having an operator, some type of tool involved. So again, identification of various equipment types capable of performing the elemental operations, and you have options that are manual, mechanized, or automated. Step 3 includes the determination of unit production times and equipment utilizations for various operations and alternative equipment types. So now we are looking at computing the number of units that we will have to produce in order to get to a certain amount. Remember that if you plan for getting 1,000 units, 1,000 good units to be delivered to your customer, sometimes you will get some failed products or some products that are not going to perform as expected. So those are not going to your customer. Those defective items might need to go to a rework station or might be discarded. So keep in mind that if you need 1,000, you might need to produce more than that in order to get to 1,000, because you need to account for those defective products that are going to happen in your process. So we need to understand and determine the unit production times and the equipment utilization for various operations and alternative equipment types in order to say, or in order to compute the expected performance of all the alternatives, and then based on that, make a decision, not only based on the performance, but also considering the cost and also the times or the schedules. So the utilizations are inputs into step 4 of the procedure, which is going to go next. Step 5 involves an economic evaluation of alternatives equipment types. And the results of the economic evaluation as the basis for step 6. Okay, so this goes in detail, explaining these 6 steps that we discussed in slide 17. So at the end, you want to make a decision, and the results of the economic evaluation are the basis for you to make that decision in step 6. The output from the process selection procedure are the processes, equipment, and raw materials required for the in-house production of products. Output is generally given in the form of a route sheet. Okay, so this output is summarized and given in the form of this document. And I'm showing you an example here at the bottom of this slide. Table 1 is the route sheet data requirement. So you have 2 columns. We have the data, includes the component name and number. So as an example, that could be a plunger housing. The operation description and number. You have the operations that are going to be needed for that component. So shape, drill, and cutoff. What are the equipment requirements you will need for this? An automatic screw machine and appropriate tooling. What are the unit times? So you need setup time of 5 hours, an operation time of 0.0057 hours per component. So this setup time is very important. This means that if you are transitioning from a different product, your manufacturing process, let's say you're building smartphones and now you're going to build computers, you need to have some time in between to set up the process. And that's what we're referring to here. So if you are moving from one product in your manufacturing line to a different product, you need some setup time, and that has to be accounted for. So 5 hour operation time, 5 hour setup time and operation time, 0.0057 hours per component. So it's gonna take, if you are doing 100, then it's gonna be 100 times 0.0057 hours. And the raw material requirements is a 1-inch diameter times 12 feet aluminum bar per 80 components. This route sheet in figure 9 for one component of the airflow regulator. Okay, so we have operation number, the operation description, and the machine type that is going to be used, tooling, the setup time. So we discussed this first piece already. This was for 0104. But then we have an additional list of operations that are part of also of these product. So we have the machine slot and thread, the drill 8 holes, the burr and blowout, and the closed subassembly. Each one of them has a machine type requirement tooling, a setup time, an operation time, and materials or parts. An assembly chart is another very good tool that we can use to get an idea of the sequencing required for the processes. This provides the method of assembling the product. And the idea here is that instead of just having words, you have like a network that is showing you, or a graph that is showing you the connected pieces in order for you to get to the final product. So for example, here we have the part numbers, right, with the names. And you know that you're going to require to do some sub-assembly of these pieces before you can move to these assembly here, because you need this sub-assembly to attach this part. And then once you complete this assembly, you have another assembly here, assembly number 2. You have another one here, assembly number 3. So you're basically connecting A1 with the lock unit in assembly 2. And then in assembly 3, you are connecting this assembly 2 with the pipe plug. This right here is representing an inspection. So that's the meaning of the box. I1 is inspection 1. You are doing an inspection of this assembly 3. And after the product is inspected, then you put it into the packaging materials for the customer. So the easiest method of constructing an assembly chart is to begin with the completed product. In this case, that will be this final assembly, and to trace the product disassembly back to its basic components. Okay, so before you got into this, you did an inspection, and before you did the inspection, you assemble this pipe plug, and before you assemble that pipe plug, you assemble this, and before you assemble that, you assemble this assembly, and then you continue going back until you get to this point.
Wait, where does it start again?
So if I understood your question, what I'm just discussing right now is what would be the best way to create an assembly chart like the one that I'm presenting in figure 10. So so if you want to create a figure like this one, the best way for you to create a graph like this one is to trace back the pieces that were needed for the final assembly. So in this case, that final assembly, if you were to create this drawing from scratch, you would have to start with A4, or the final assembly, and then understand, okay, before you get into this final assembly, what was the last thing that you did? The last thing that you did was to put the final product into the packaging. So if you take the product out of the packaging, what was the last thing that you did? Before you put it into the packaging, the last thing that you did was an inspection. And before you did the inspection, what was the last thing that you did? Well, the last thing that you did was to put this assembly 2 together with the pipe plug. So what I did was put that previous assembly together with this pipe plug. And then you continue that process So before you attach the pipe plug, what did you do? Well, the previous step was to connect the lock nut. Okay, so the previous step was to create an assembly in which you attach this component, 4250 lock nut. And before you attach the lock nut, what you did was you did an assembly with the body. Right, so the body. So you put together this sub-assembly with the body. That was what you did in assembly 1. Okay, and then the only thing that is missing here is this sub-assembly. So what are the things that are needed to put that sub-assembly together? Well, you need all these pieces. So that's what you're going to be putting in here. So going back to that comment in the gray box, the easiest method for constructing an assembly chart is to do what I just did. You have to understand the sequence of steps that are required for the final assembly, and then you trace back those events or assemblies you reorder those from end to beginning in order to trace back each part of the assembly until you get to the original components. So does that answer the question?
Yes, it does. Thank you.
Okay, good. An assembly chart does not provide an overall understanding of the flow within the facility. It's just telling you how things are organized or what is the right sequence for putting together the final product. By superimposing the route sheets on the assembly chart, a chart results that gives an overview of the flow. And that is called the operation process chart. So here's an example of the operation process chart for the airflow regulator. So now you are putting also information about operations that are needed for each one of these components. So for example, here for the, let's see if I can see, where's the plunger retainer here, 4150. So this is the plunger retainer. This is one of the components that are part of this first sub-assembly. So we have the 4150 plug-in retainer, and we have information about the operations that are needed to create this plunger retainer. Then we have the seat ring. That's 3250. 3250. You have information about the operations that are needed to get that done. And if you move forward into that process, you get information about the plunger housing also, 3254. So what are the operations that are needed? These are 3 operations. They're listed here. And it looks like these 3253, 3251, and 3555, these are pieces that we are purchasing. So we don't have to perform these operations. So we do the sub-assembly. All the information about this group right here is now also here, but it's giving you additional information about operations that are needed. Plunger housing. Oh, it's also part of it. I apologize. The plunger housing is also part of this group. So this should be containing here. And then the rest of the, so it looks like these are the pieces that we're manufacturing in-house, and the rest of the components we are purchasing. So this is the information that we will need in order to design our facility. So these are the operations that are going to be creating the operations that are going to be part of the process for assembly and also creating the parts that are needed for this final product. So the idea here again is to, if you want to get the information not only about the components that are part of the final product, but also about the operations that are needed to get that final product, you can use the operation process chart for that, which is you're basically taking this diagram and putting the information of the route sheet inside this diagram to create this final diagram. To construct an operation process chart, begin at the upper right side of the chart with the components included in the first assembly operation. If the components are purchased, they should be shown as fitting horizontally into the appropriate assembly operation. If the components are manufactured, they should be shown as fitting vertically into the appropriate assembly operation. The operation process chart may be completed by continuing in this manner through all the required steps. This is until the product is ready for release to the warehouse. A second viewpoint based on graph and network theory is to interpret the chart as a network representation. And we study network representations in IE 3340 operation research. So if you're an industrial engineer major, you might have an understanding of these network representations to solve problems. If you are a manufacturing student, you might not have that background, but the idea is to use this network representation to allow us to have a better understanding of how these processes are connected to each other to design the final product. So the presence diagram is a directed network and is often used in project planning. The presence diagram shows part numbers on the arcs and denotes operations and inspections by circles and square, respectively. So this is what this presence diagram for the airflow regulator looks like. So you have these pieces happening simultaneously, and then at some point you see that the final assembly is more like a straight line in which it's fed by only one arc. But at the beginning, you have all these arcs that are connected, that are needed for you to get to the first assembly. And then after the first assembly is just one link or one arc feeding each one of the assembly 1, assembly 2, assembly 3, and assembly 4. Okay, so this is just a visual representation. I'm not gonna ask you to build a presence diagram for a product, but you need to understand what this is representing. So at least see, okay, if you are faced with something like this, you understand that these circles are representing something, that the arcs are representing something, and the shapes are representing something else. Okay, so the part numbers are on the arcs. Denotes operational inspection by circles and squares. So if you see this here, part numbers and the operations, right, are in circles, and the assemblies, and then the inspections in squares.
Could you go
Good.
back to that last page real quick, just so I could see what, you see the part numbers on the arcs, one more page back? And so the operations inside the circles.
Whoever's
squares,
talking, I can't hear you.
Excuse me?
The operations inside the circles and squares.
Yes. So this parts, let me go back here. So remember, from the operation process chart, you have the part numbers. Let's say that, let's look at this one, the plunger housing. You have 3254, that's part number. And then you have these operations that are needed for you to build that plunger housing. So you need to do the cherry drill, machine slot, the drill holes, and the bore and blowout inspect. So if we look for 3254 in here, you see that you have an arc that is fed into these operations, right? So 104, 204, 304, 404, those are these operations.
Gotcha, thank you.
Okay, so numbers, those numbers are basically codes for the things that you need to perform into this part in order to get them ready for the subassembly. So once you perform this operation in 3250, this operation in 3252, and so on, you can put those together here. And the ones, I'm sorry, as I'm in the Ingram Hall and siren, I don't know what that means. I apologize for that. So for the ones that there's no circles, like 3251, 3253, and 55, those are purchased. So these are not parts that you're building in-house. So that's why there's no operations associated with them. Same thing here at the top. So those are coming from the supplier, and you're just adding those into the assemblies. Okay, so the last part of this lecture is on the schedule design. So we talk about product and process design. So schedule design decisions provide answers to questions involving how much to produce and when to produce. Production quantity decisions are referred to as lot size decisions, and determining when to produce is referred as, excuse me, production scheduling. Okay, so now what we are trying to say is, okay, I now have an understanding of how the product is going to look like. I have an understanding of the sequence of processes that needs to happen in order for me to build this product. So the third part, which is what we're discussing now, is, okay, so if I need to assemble this many products, I need to determine how many to produce to begin with in order to get that final number of products delivered to my customer. And remember, this is connected with what I just mentioned in terms of defective rates. So you might need to produce an excess of units in order to get that final number, because you will get some defects into your process, and those defective products will be sometimes they will be discarded, and sometimes they will be reworked. So in addition to how much and when to produce, it is important to know how long production will continue. Such a determination is obtained from market forecast. Specification of process requirement typically occurs in 3 phases. The first phase is to determine the quantity of components that must be produced. And this includes allowances for defective items. The second step or phase is to determine the machine requirements for each operation. Number of machines, for example, like if you're gonna have a stations of drills, how many drills do you need in that station in order to get that final number of parts that you need to deliver to the customer? And then the third phase is combines the operation requirements to obtain the overall machine requirements. So for example, if you need an operator managing these machines, let's say you have 10 drills, and these drills, once you're completing a part in one of these drills, you need an operator to go pick up that part and put the next one. That's what we are considering in this third phase, the operation requirements. So you might have the machines, but if you don't have enough operators to run those machines, that's not going to make a difference. So you need to in addition of planning for the number of machines, you also have to plan for the operations around those machines. Because if you don't have enough operators, those machines could be idle most of the time. But if you have more than enough of operators, then you will have some operators that are idle at some points during the manufacturing process. So the idea is to find that balance in which you don't have operators that are idle or machines that are idle. So you have to come up with that benefit cost ratio. Which ones do you want to starve? Do you want the operators to starve, or do you want the machines to starve? What's gonna be less expensive for you? So today we're gonna talk about the first phase, which is the calculation of production requirements. And this looks at the required inputs to manufacturing and assembly operations. And those can be computed or determined as follows. We're gonna have a DK that is gonna represent the percentage of defective items produced on the kth operation. So if you have 3 stations, how many defectives are you expecting in each one of these stations? So K is gonna represent the station. K equals 1 is station 1, K equals 2, station 2, and so on. So we're gonna have a defective rate associated with each one of these stations. OK is the desired output without the defects. So if at the end you wanna have 1,000 units, that's your desired output. And IK is a production input. So how many do you need in order to get to that desired output? So we have some equations here. On average, or on the average, that desired output, OK, is going to be equal to the product input minus these DK times IK. DK is the defective rate times the production input, which can be solved or rearranged into this expression. Therefore, since what we're trying to find out is IK, we can solve for IK, and that will give us this expression. We know, if we know the desired output and we know the defective rates, then we can solve for the input that we would need it, or that will be needed for production. And this is basically, this expression is designed for a single station, right? So if you have a single station, this will be OK, this will be IK, and then you have the defective rate. Okay, so if you're familiar with circuit analysis, is the same idea. So you have an input and output, you have a resistance, so that will be the defective rate. The idea again, if you know this and you know this, then you can compute this. For products with n sequential operations, let's say something like this, you have station 1, station 2, station 3. You have a defective rate. And then this will be input 1, input 2, input 3, and this is output 3. We have something like this. The expected number of units to start into production at the first operation is shown in the relationship below. So it's the same idea. Now we can show that ON is going to be equal to I1 times the number of defective rates in the 1 minus the number of defective rate, or the defective rate in station 1 times 1 minus the defective rate in station 2 times 1 minus the defective rate on the station N. And we can also solve for I1, which is the expression that we have here. Remember, I1 is what we are looking for. What will be the input needed for you to get this desired output? And here I have an example. So we're going to work through this, and then this is the last thing we're going to do today. So in this example, we are calculating the production requirement for a serial process with 3 operations. The product has a market estimate of 97,000 components and requires 3 processing steps: turning, milling, and drilling. And we have the defective estimates. D1 equals 0.04, D2 0.01, and D3 0.03. The market estimate is the output required from step 3. Okay, so what we're going to do is, knowing this, we need 97,000. How many we need to begin with in order to get to that desired output? So we have 3 processes. This is process 1, process 2, process 3. And then we want to know what is this input 1. And we know that the desired output is 97,000. And we know that D1 equals 0.04, D2 equals 0.01, D3 equals 0.03. So using the tools, and remember, here, this is going to be output of 1. Output of 1 is going to be the same as input of 2. And this output of 2 is going to be equal as the input of 3. And our output of 3 is given, 97,000. So I need to know what is this, this, and this in order to get this number. So I'm going to start backwards. Going back to this equation, right? I know that IK equals OK divided by 1 minus DK. So I know O3. So I'm going to solve for I3. I3 is going to be equal to O3 divided by 1 minus D3. So I3 is going to be equal to 97,000 divided by 1 minus D3, which is 0.03. So this is equal to 100,000. So I know I3 now, And since I know I3, I also know O2 because O2 is equal to I3. So now I can compute I2. I2 is going to be equal to O2 divided by 1 minus D2. So I2 is 100K divided by 1 minus 0.01. This is equal to 101,010. And finally, since I2 is going to be equal to 01, I can find I1. I1 is going to be equal to 01 divided by 1 minus D1. So this is 01 is going to be 101,010 divided by 1 minus 0.04. And this is equal to 105,219. So this is the number of units that I need. I need 105,219 units. To begin with, if I want to get these many units, 97,000 good units at the end of the process. Okay, so this is basically telling me that you have about 8,000 units that are going to be defective and that we cannot deliver to the customer. If you want to use this equation instead, we can do that, right? Because this is a sequential process as the one that we show here. So if we do I1, we know O3, which is 97,000. And we divide it by 1 minus D1, which is 1 minus 0.04 times 1 minus 0.01 times 1 minus 0.03. This is going to be the same, 105,219. So since this is a sequential process, you can also apply this equation to solve the same problem. You will get the same answer. And that's all I have for today. Do you have any questions?
I think it's worth mentioning in the current supply chain environment that we may want to make sure that we could withstand any supply chain shortages if we're planning a facility.
Yes, that's a good point. So getting enough products into the production schedule so we account for those possible shortages in the future. Very good point. Any other comment or question?
No, sir.
Good. So I'm going to stop now. And if there's no questions, then I'll see you on Wednesday.
Have a good day.
You too.
Thank you, Professor.
Thank you.